Thank you, everyone. Well, thank you very much for coming out on Wednesday evening for the couple lecture hosted by KIPAC, the Catholic Institute for Particle Astrophysics and Cosmology. My name is Sanju. I am the Outreach and Engagement Manager at KIPAC, and I will also be your host tonight. So it's very exciting to see all of you in person today. I see many familiar faces. Thank you. And I also see a lot of newcomers. So welcome. At the same time, we're also welcoming the similar the group online that is watching the live stream right now. So either way, we hope that you take away some exciting discoveries from tonight. And I am also personally very excited to introduce today's topics to you. As some of you already know, we typically collect feedback after our talks, where it would also include the kind of topics that you would like to share from us. And this topic is exactly selected in that way. So there was a lot of interest in the audience feedback about dark energy. I know it's so mysterious. And we just felt that now, especially, it's really the timing to feature some of the latest results, especially that we just had one major multi-year survey that has recently concluded. And, so there will be some very new interesting findings presented to you tonight. So tonight, as I mentioned, we will be learning a little bit more about dark energy and cosmic exploration, and also how we use galaxies as key probes to decipher some of the most mysterious aspects of the universe. So before we start, I would like to give a really big shout to the entire team who is supporting this event behind the scene. So those included the front desk staff members, many of you have already interacted with. We have the tech team here supporting this event. Leon here is managing the live stream. And because this is a hybrid event, we also have online chat moderators to also help answer questions as they come during the presentation. So these online chat moderators are subject matter experts also on this topic, and they are going to answer most of the questions that come in line. I will give them a chance to say a quick hi to everybody. All right, first we have Rebecca.
Hi, everyone. My name is Rebecca. I'm a postdoc at KIPAC, and my research focuses on using supernovae to understand the expansion history of the universe.
Great, thank you. We also have Shenshen.
Hello, everyone. I'm also a postdoc here at Stanford. I use weak gravitational lensing effect to study the universe. Happy to be here.
Great. Last but not least, we have Theo.
Hi everyone, I'm Theo. I'm a final year PhD student here at KIPAC. I also work on weak gravitational lensing with Agnès on DES.
Awesome. Well, thank you all. And you might have heard, terms of weak gravitational lensing or DES or supernovae. Don't worry, Agnès talk will answer all those questions. Okay, so that's a kind of a hook that we have here. So for those of you joining online, all these chat moderators, they will answer most of the questions as the talk goes on, and feel free to use the live chat box that you see on the right-hand side to engage in discussions and ask all the questions that you have. We will also have a few questions from the online audience saved for the dedicated Q&A time at the end of this talk. And for all of you in person here, you are all welcome to submit your questions for the Q&A time, and even afterwards to talk with Agnès, and then also all of our chat moderators in person after the event. So all of our chat moderators, they're also going to be in person here in case you also have follow-up questions or wanted to ask any questions. So now it is my great pleasure to introduce tonight's speaker, Dr. Agnès Ferté. Agnès is a research staff scientist at SLAC, and she specifically uses large-scale galaxy surveys to study dark energy and also gravity. She got her PhD in France from Université Paris suit, and also got her postdoctoral work done at the Rubin Observatory in Edinburgh, and also the Jet Propulsion Lab in Pasadena, California. Most recently, she has been working to ensure the high quality of data taken by the Rubin Observatory, as well as designing some of the most precise tests to date of gravity that are on cosmological scales. I was specifically very moved by Agnès' personal story about how she got into astronomy. She actually read about the expansion of the universe on a magazine when she was a teenager, and that has been a motivation that has, driven her to be an active player in this field. And this path has now led her to actively working in this specific field, and she just feels very fortunate to have the opportunity, taken the path, and she just can't wait to share, the new knowledge with all of you. So without further ado, let's welcome Agnès.
Thank you.
Hello everyone, thank you so much for coming in person or attending remotely. Thank you so much for the very sharing and Theo to have me tonight. I will devote a lot of questions to you. I'm incredibly thankful and honored to be here and to get to tell you about the remarkable progress in cosmology over the past few years. Oh, that's my baby. When you start looking at the sky on the largest scales, you don't really care about a specific planet, a specific star, a specific galaxy. You start seeing many, many galaxies, and you start to be able to say something about the properties of the universe. And this is the field of cosmology. Modern cosmology started around a century ago, when Einstein proposed that gravity is actually just a geometric effect in his theory of general relativity. A mass will curve space-time. So I just had a baby, she's in the back, and I've already been reading to her about GR. Okay. Sorry. Okay. Okay. So thanks to this amazing book, this is a ball. A ball has a mass, more ball, less mass, less ball. It's easy. GR is easy. You don't need to know about it. So around this time, Friedman applied Einstein equations to the universe and was able to describe the universe. And what's mind-blowing to me is that at that time, we didn't know there was anything else beyond our own galaxies, the Milky Way. We thought that's all there was in the universe. And it's easy to think that the history of cosmology was just made by men, but in fact, women were always there, making also great progress in science. And one of the discoveries was by Henrietta Leavitt, who was the first to propose a new way to measure the distance of astronomical objects, other than using the parallax. And so this was the first huge step before the discovery by Hubble that the further a galaxy is, the fastest it recedes away from it. What does that mean? It means suspense. Okay, thank you. Okay, so what does it mean? The further a galaxy is, the faster it's moving away from us. It means the universe is in expansion. It has been in expansion for the past 13.7 billion years since the Big Bang. And what does it mean? It means the universe has a story. It's changed as it's evolved in time. In fact, today, we know that only 5% of the universe is made of normal matter, what makes us and everything around us. Because in the 80s, in the 70s, and in the 80s, a great woman again made a further discovery that there is more matter than we can see by measuring how fast stars move around the center of their galaxy. Instead of their velocity dropping as they get away from the distance of galaxies, the velocity is staying actually flat. That means there is more matter that we can't see. This matter, we call it dark matter, and it makes up 85% of the matter in the universe. It makes those wispy filaments, what we call the cosmic web, and forms sort of like cocoon where galaxies form. And this forms the large-scale structures of matter in the universe. And then later on, in 1998, two different teams used supernovae, which are stars that exploded, to measure their distances and velocity. And they have shown that although we think if a universe is mostly made of matter, the expansion should slow down with time because of the effect of gravity caused by that matter. But they're showing with this data that actually there is not just matter. There is something that we call dark energy. And you might think, okay, those data points here that are showing matter plus dark energy, they are all over the place. Come on, this is not saying there is dark energy. Well, since then, and by the way, they got the Nobel Prize for this huge discovery. Since then, we have shown again and again, and this is again with supernovae, but now 1,000 supernovae instead of the 50 supernovae that they use for the discovery. Clearly, the expansion of the universe has been accelerating with time. The expansion is going faster and faster with time. There is a dark energy. And today, most of the universe is made of that dark energy, 70% of the universe. In the consensus today is to say that dark energy is a cosmological constant that's kind of driving, it's kind of like the energy of the vacuum driving those galaxies apart. You can think of it as just adding a constant in Einstein equation of general relativity. So as a whole, if we take all of this together, we have what we call the Lambda CDM model. So to describe the universe, gravity is described by GR. There is normal matter, dark invisible matter, and a lot of dark energy today that's dominating the universe, because we see that the universe expansion have been accelerating for the past 5 billion years. And when we take all of this together, we can actually describe the universe with just 6 numbers. 2 of them are the amount of matter there is in the universe. And the other is how this matter clusters, like the clumpiness of matter of the cosmic web. And one of the predictions of the Lambda CDM model, of the Big Bang model, is that there is a light coming from the Big Bang that we can actually detect today. This light is everywhere around us, and it comes from the Big Bang, the origin of the universe. And this is how this light looks like, the different colors that corresponds to different temperature. And there was a talk about it a few months ago, if you remember. So you can see that there is a typical scale for those temperature fluctuations. If we look at the power, how much power there is in those tiny fluctuations, you see this typical scale, it shows up as 1 degree in the power of this light. If I lost you here. The most important thing to see is that the measurements of the power of this temperature fluctuation are in red, and the Lambda CDM model is the green line. It follows exactly the measurement that we have of the cosmic microwave background, the light from the Big Bang. And then if we multiply our cosmological observation, if we start looking at other cosmological probes, then it's always the case. The Lambda CDM model, the line, is going through the data points. It's absolutely beautiful. It's amazing. All of these are completely different cosmological probes. So the Lambda CDM model is really the consensus to describe the universe today. However, there are a few problems, like what we call the cosmological constant catastrophe, where if you want to predict the value of lambda, that cosmological constant with mathematics, you get an error of 120 order of magnitudes. That's a pretty huge mismatch. In fact, this author called it the worst prediction in physics. So this is a tiny problem. Then really one of the most important progress in the field of dark energy that has been made over the past 2 years is that for the first time, we are seeing hints that dark energy that's causing cosmic acceleration is not constant. It's varying with time. It's actually weakening with time. The acceleration is less and less with time. So this is showing the value of the dark energy today here and the time dependence. And here the cross corresponds to the Lambda CDM model. And you see all of our data are away from this cosmological constant. And I'm going to try to explain this plot later on a bit more. So what is causing this cosmic acceleration that has happened for the past 5 billion years? Is it that dark energy is not a cosmological constant? It's a weird fluid. We don't really understand what it is. So we need to understand measure its property. Or is it that GR is wrong, that the laws of gravity on such cosmological scales are different than what we think, that GR is incomplete on those scales? And this is actually one of the things I've been working on over the past 10 years. So why do we care? Well, the properties of dark energy completely kind of like define how the universe is going to evolve in the future. If dark energy was like increasing with time, then we would have the big rip, literally ripping space-time. If suddenly dark energy sort of disappeared, then gravity would kind of pull everything together and we would get the big crunch. And then additionally, if GR is wrong, that is a huge, huge shift in physics. We would have to develop a new theory of gravity. And we have to use GR to predict a lot of things like the clock ticking rates on satellites for the GPS. So it is very important to understand what is causing this cosmic acceleration. So we can test the Lambda CDM model and the dark energy and gravity, either by looking at this light from the Big Bang, the CMB, the cosmic microwave background. And this has been the goal of the Planck satellites that produced this map from space. And this is the most precise map of the CMB. And today, there are other efforts to measure the temperature and the polarization of the CMB with the ACT and Simon Observatory in Chile and with SPT and Bicep Cake at the South Pole. But then we can also observe the universe 13 billion years later, looking at the evolved universe. So the tiny fluctuations that we see here in the CMB, they correspond to the density fluctuation that were produced just after the Big Bang that got imprinted on the CMB. And this density fluctuation evolved while the universe expanded to form this cosmic web I was referring to earlier, the large-scale structures in the universe. So we can probe Lambda CDM and dark energy and gravity through those large-scale structures. And so this is the goal of a new generation of cosmological surveys, like the NASA Roman telescope that will be launched in September, one of the rare telescopes that will launch ahead of schedule. The Euclid satellite from the European Space Agency that is taking data right now from space, the DAISY experiments from Arizona, and finally, the Rubin Observatory from Chile, which I will tell you more about later. It was also a huge goal of the Dark Energy Survey. So the Dark Energy Survey, or DES, was a survey of 10% of the sky from Chile, here from Cerro Tololo, on the Blanco 4-meter telescope. And the power of DES was to use a huge camera developed especially for that purpose. This is a DCAM camera. So we mapped the sky, 10% of the sky, from 2013 to 2019, which starts to be quite a while ago now, but we completed the survey. And this is me here at the telescope. I was very lucky to be part of the observing campaign. I went there for 2 weeks to make sure that the data taking was going well. So that was, it is pretty rare for cosmologists to be able to go at the telescope, and that was a huge experience for me. What was not as fun was to see the gigantic spiders in the Chilean deserts. Like, it was a great time anyway. So the DES was actually one of the first very large collaboration in astronomy. We had around 500 people working at the peak of the time when DES was working. So this is a picture of the collaboration last year. So we have produced a huge legacy of scientific achievements, some of them about the test of the Lambda CDM model. This is an article I collated with one of my colleagues, also from KIPAC. And one also discovery that I really liked from DES was the discovery of a giant comet that was going around. So this is the sorts of images that we took, so where each dots are galaxies. And here you can see a few stars. You can recognize them because they have spikes around them. And the colored stripes here are things that are moving, like asteroids. So what can we do how do we test dark energy and gravity from this sort of images? So first of all, you can measure the distances of objects or to then infer how fast the universe has been expanding. But it's actually really hard to measure distances in an expanding universe. So what we do is we use what we call a standard ruler. So I told you that the CMB has this 1 degree scale, like it has a peak at 1 degree. Well, that scale is growing with time. And we can see today it's imprinted in the way galaxies are distributed in the sky. And so that's a fixed scale that's growing with time. So if we measure that scale at a specific time, then we know how big it is intrinsically, so we can infer how far away it is. And on the other hand, we can also use standard candle. Supernovae, for instance, so dying stars that have exploded, have intrinsic brightness. So if they are fainter, then we can tell that they are further away from us. So we can also estimate their distances. But also, we can also probe how the cosmic web, the large-scale structures, are evolving with time. This is an example of a simulation showing that just after the Big Bang, we have this sort of like soup of matter that evolved with time to form the wispy cosmic web that we see today. And this evolution depends on the properties of dark energy. This is, again, a simulation that shows here in blue how matter is distributed in the Lambda CDM model, in the normal model of cosmology. And in orange, it is how is a structuration of matter in the case of a time-varying dark energy. And of course, gravity will also completely determine how matter is structured. And this is, again, a simulation showing on the left the case of GR, and on the right, if you modify the laws of gravity, it will completely change how matter is structured. So the redder means there is more density, there is more matter. So you can see it changes the substructure of matter. The problem is, I told you, most of the matter in the universe is not visible. It's made of dark matter. So how do we actually measure that instead of just simulating with computers? How do we probe the cosmic web? We have to use indirect ways to do it. One way is to use galaxies as tracers of the cosmic web. They're like kind of like the tip of large iceberg of dark matter that we can see, because galaxies form where there is dark matter. And there is also another effect. It's the weak gravitational lensing. And again, we have GR for babies to the rescue, where a particle has like light, has to follow the shortest path through curved time. So if there is a mass, the light from a faraway, if there is a mass, yes, the light from a faraway galaxy will be deviated because of this mass curving space-time. So we can use galaxies as a background light. So this is called the weak gravitational lensing. And its effect is to modify the shape of galaxies. This is a little GIF I made of where I lens, literally with a lens, a grid, and you can see how it's modifying the shape of the grid. And this is exactly what happens. So this is, for instance, an image from JWST, showing here galaxies that are completely distorted because of the mass between us and those galaxies. But what I've been, and so we can use gravitational lensing to reveal where dark matter is, because you can look at what is distorted, which galaxies are distorted, and infer the mass between us and those galaxies. So we don't know what dark matter is, but we know where it is, thanks to the gravitational lensing. But in my research, I've used the case of the weak gravitational lensing. So instead of those like very strong extreme lensing effect where we see those huge arcs, this effect is the lensing of galaxies by the cosmic web. So those gigantic, tiny, like those gigantic low density filaments or nodes of the filaments. So this is called the weak gravitational lensing because it's just a 1% effect on the galaxy shape. And how does it show up? It shows up as the coherent deformation of the galaxy shape. The galaxies appear more elliptical in a coherent way. Because this effect is so tiny, we need to image millions of galaxies. For instance, with the dark energy survey. So that was one of our goals, was to use weak gravitational lensing to test dark energy and gravity. So from this data, there is a huge sort of like pipeline, a huge amount of work that goes from getting those galaxy images, then building our measurements, and then finally inferring what are the values of those numbers that describe the Lambda CDM model. What are the values of the cosmological parameter? How much is there matter? How much the matter is clustered in the universe? And here I'm showing kind of like the very final step where we infer, given our data, what is the most likely value of those cosmological parameters in the universe? So this is why I'm showing always those sort of like two-dimensional plots where the more color we see, That means it's a more likely value of the cosmological parameter. So it is a huge challenge to go from imaging the sky to getting those measurements of the cosmological parameters. In fact, the dark energy survey was proposed in 2005. So it took us 2 decades of work to go from proposing the dark energy survey to actually getting our constraints on dark energy and gravity. And this has also seen many generations of scientists, and I'm very grateful I was part of it with many other early career scientists like PhD students and postdoc, because we really developed our skill in analyzing those data, which will be extremely useful for the future. And also it's been also fun to work on this beautiful data. And this is a link to the publication if you are interested to read more details. So we have completed the survey, but we have been working up to this year to produce the final results on cosmology and dark energy using this completed survey. So this is our final results. This is our measurements using weak gravitational lensing in the full DES survey, the full map of the 10% of the sky, where we measure the matter density and how clustered the matter is in the cosmic web. And so this is showing the results in pink and the results from the CMB, the light from the Big Bang, in blue. What can we see? Well, we can see that actually those 2 contours are pretty similar. So that means we are able, with the Lambda CDM model, to predict both the CMB just after the Big Bang and the universe today, 13 billion years later. So this is a huge win for the Lambda CDM model. Also, I will just note that you might notice that, okay, they are actually not exactly overlapping. They are not measuring exactly the same value of the clustering and the amount of matter. And this is a known sort of problem that there is a very slight mismatch between the 2. But statistically for us, it's not a huge deal. It's basically consistent. I mean, we're talking about a separation of 13 billion years between the 2. This is pretty good to me. Okay, so this is from this year. So this is really the latest on the topic. And now we are finally testing dark energy properties using the full DES. And this is the first time that we have been able to measure the properties of dark energy with a single survey, because the results I have shown you before, they were combining different type of measurements. But this is a different type of experiments. But here, this is showing, well, you don't need to understand all the details. It's showing different type of combination of the data. And we have shown that using only the DES supernovae, standard ruler, and weak lensing, that there is a hint for time-varying dark energy as well. Again, we are away from the cosmological constant lambda, but we are less away from Lambda CDM than the previous experiments 2 years ago. But still, it seems like there is something here. Now, we are closing the DES chapter and we are going into the next era of this new generation of cosmological survey like Euclid, Roman, DESI, and the Rubin Observatory. And this is one of the results from one of my work showing that in testing gravity, in measuring deviation from GR, we can expect an improvement of 1 order of magnitude in our measurements of deviation from GR using weak lensing from the new surveys. So this is a huge motivation for me to kind of like keep working in this field and be part of the new generation of experiments. So one of those experiments is the Rubin Observatory. The Rubin Observatory is a new observatory in Chile, actually just on the mountain next to where DES was. It's located here in Chile. So it's been in the work for a long time. Again, it was proposed around the time of around 2000. In fact, funnily enough, it was proposed at the same time as GS, and it was predicted that they would be concurrent and that GS would be worthless because LSST will be there. And it's happening just now when GS has been done for 6 years. So it tells you about the timescales of research. Sometimes things can take a very long time. So there is a new observatory, a new building with a 8-meter telescope, very compact, and with a 3-mirror system. And actually, I 3D printed last night the building, the Rubin Observatory. The 3D model is available online. I don't know how to 3D model. I just sent it to the printer, and it worked all night to do it. So you can check it out after. You feel free to look at it. And yeah, it took 11 hours, so it tells you how big that is. Okay, so the main goal of the Rubin Observatory is to produce the legacy survey of space and time, the LSST. And so what is the LSST? It's a 10-year long survey that is going to start this year. It has not started yet, but we expect it will start very soon. And it will map the whole southern sky, again, in optical, so in visible light. And it sort of has 2 modes because it's extremely fast. The Rubin Observatory is extremely fast at moving the telescope and mapping. It maps a large part of the sky at once. So at the end of those 10 years, we will have 800 maps of the entire southern hemisphere sky. So this is huge. That means we will have sort of like a movie of the sky. We will have access to transient phenomena, things that either explode, like supernovae, or things that move, like comets. But on the other hand, because we will revisit the same part of the sky many, many times, we will have deep images of the sky, which we call the static sky. We will have beautiful images of the sky. And at the end, we will have now billions of galaxies that we will be able to use to measure this weak gravitational lensing effect. So the main instrument of the Rubin Observatory is LSST-CAM, which is the largest camera ever built. And it was built here at SLAC, the lab, the national lab associated to Stanford. And this is showing it has 189 CCDs. And this is showing the sort of images that just a tiny part of this huge camera is able to image so many galaxies in just a few hours. So it's just going to be mind-blowing images that we're going to take over the coming 10 years. So because it's such a large camera, so it has many pixels, and it's taking so many data, so many images of the sky, it's going to be a huge data challenge to analyze its data. We actually expect 20 terabytes of data per night, and we expect that there will be detection of 10 million transient objects per night. So that means we need to develop fast pipeline, parallelized computing. We need to be able to send those data on the network and to distribute those data. This is a huge challenge, and there are actually many scientists working on those problems. And in my research, one of these data problems is the fact that doing this inference, so going from the data to actually what is the number to describe the universe? What are the properties of dark energy? What is GR correct or not? To do this step, it actually requires millions of CPU hours. Your laptop probably has 8 CPUs. So you can imagine this takes a very long time, although we use parallelized computing with, for instance, 200 CPUs or 500 CPUs. And this is just for one bit of the analysis. Of course, there are so many more things like simulating the sky, etc. So this is a huge problem, and it's really limiting our ability to explore beyond the Lambda CDM and to explore new physics. So one way to solve that problem is to use neural network to be able to quickly emulate different universe, and this way to be able to accelerate that step. Another thing is to be able to use those neural network to kind of decide which alternative to the Lambda CDM model to use to test our data. And this is something I have proposed to do, and I think will be very useful to decide what, for instance, alternative to GR we should consider to test with the LSST data. So I feel extremely lucky to be working in cosmology right now at this time, because it's sort of like the convergence of three different things. We have new tools like machine learning or the development of new computers. We also have this huge potential paradigm shift, and also a huge deluge of cosmological data that are coming. And I've been also very grateful that I've been able to kind of get ready for this era by working within the Dark Energy Survey. So I hope tonight I made you feel part of this adventure as well, and I thank you for listening.
Great. Thank you, Agnès. Let me just turn on the lights. I know this is a very informative talk packed with information, and probably you'll have a lot of questions, and perhaps we can also move our thing out of the screen. So we're going to first take some questions from all of you in person. We also got a few questions already lined up online. So any questions for Agnès? Okay, I see a hand over there. I have a question on what regard for network you mentioned salaries analysis and handling and university.
Yes. Oh, I'll also repeat the question. So perhaps, if you want to go to the slides. So the question was what are the tools? Is that what you're asking? Oh, okay, cool. Yeah, so you introduced in the last part the neural network. How exactly do you use that to actually do any of the work that you showed us, especially turning that into a control plot? Yes. So so that allows me to explain this a bit more. So that's great. Thank you. So the way we actually measure, we infer the value of those cosmological parameters is by trying different location in different values of this parameter and actually compute the weak lensing signal at each of those points. And this takes a long time. I mean, it takes like a second, but we don't do it on just 2 parameters. We do it on 60 parameters because we need to take into account uncertainties that we have on our measurements. So we need to be able to kind of evaluate the weak lensing signal at each point. And the neural networks can be very useful to sort of predict the weak lensing signal for any combination of parameter values very quickly by training them on we predict the weak lensing signal for different known values of this parameter combination. And then we can use those neural networks to predict any place on those parameter combination.
Hope that answers your question. Okay, I see a hand over there. But the dark energy is changing over time. Is that because the universe is itself in a different phase of time, or is there more?
Okay.
So the question was, you showed us the plot. One of the biggest results was that, dark energy is changing over time. So how did you actually get to that point to know? And, was it because of any measurements that you did at different slices of cosmic time that you got that result?
Yes. So first of all, I want to say it's not completely sure that time is that dark energy is varying with time. It sort of like hints that it might be happening. And what we are using is those supernovae, the weak-lensing as well. And so the supernovae will appear differently will appear differently to us the further away they are if dark energy is varying with time. And similarly, the weak-lensing signal will be modified because maybe I can try to explain this with this plot. So those galaxies that are far away, they emit their lights, and this light is kind of filling the space-time between us and those galaxies all along that line. So it's sensitive to how space-time is changing with time. And that's directly linked to dark energy. So if dark energy is weakening with time, then the expansion rate is slowing down. The acceleration rate is slowing down with time. So that will directly impact how the light will be modified. It will expand that grid in a different way. It's so the dark matter sort of curves the space-time, and dark energy stretches the space-time at an accelerated rate.
And actually, a follow-up question on that. So you talked about, dark energy. There might be hints that is, like time dependent, right? So how do we actually interpret that in terms of, the future of the universe? Does it have any inferences on, how we actually take in that result?
Yes. So I think those results that we have means that dark energy could be. I'm very careful. I'm not saying we definitely have detected it. I'm just showing you results as they are. It could be weakening with time, which I think it means, so it will still be expanding and it will still be accelerating, but at some points, like actually, I don't really know if you look very far in the future, how it will look like, but we wouldn't get a big rip, for instance. So we would just, it would just grow with time, but not as bad as if it was, so the dark energy was getting bigger and bigger. Yeah.
Got it. Okay, so we can kind of like rest assured there would not be
There are also problems that are more urgent. That's
okay. Great. Yes. All right. I see a hand over there. Yes, with the hand.
Yeah. How to study the time axis?
Okay, yeah. So the question is like in all those plots, how did you study the time axis, right? How do you actually like map those into different cosmic times?
Yes, so the key point is to measure the redshift. So how far and how fast astronomical objects are or are receding from us. And so we can do it through different ways. So for instance, for the standard ruler or the standard candle, we can use a spectrograph to measure the spectrum of those objects. But for the weak gravitational lensing, we are imaging so many galaxies, we can't have the spectrum of all those galaxies. So we have to make sort of like supposition, or like we have to develop ways to sort of like know at what redshift those galaxies are by looking at their color, basically. So it's less precise than if we could measure the spectrum, because the spectrum is shifted as the universe expands. But it allows us to have many more to use many more galaxies. So it's by measuring this stretch of space-time through redshift.
Great. Yeah, I see a hand over there. Mm-hmm.
So, like in weak lensing, you said that we see distorted images of the universe because of PR, but to estimate the matter between it, you need like a weak lensing image and a non-weak lensing image.
Yeah. Oh, sorry.
Oh, yeah. Sorry. What? Was there a question about that? Yeah.
But we don't have an image without weak lensing, right? So how do we estimate the mapping?
Yeah, great question. Okay, so the question was, like in order to characterize the magnitude to which extent weak lensing is distorting the images, right? You got to have some kind of reference to compare with, but we don't really have that because it's already been distorted. So like in your work, how do you actually like reconstruct what was the intrinsic shape of those galaxies?
So the key points that help us here is that galaxies all have different shapes. There is no one preferred shape. So if that's why we actually need to go to image millions of galaxies, is because then we are not sensitive to the intrinsic shape of galaxies. We can just measure their ellipticity. So if you average all galaxies together, they have no ellipticity. So if you measure an ellipticity, that means that's caused by the weak gravitational lensing.
Likely approximating the weak lensing over millions of galaxies.
Yeah.
Great. And I saw some hands here earlier. Yes.
In quantum computers, they use this. I don't know what comes from the sky. I don't know it's, you know, it's not CPU. You were to superpose on a quantum computer.
Yeah, great. Question was, you know, you just presented this big data challenge, right, as we're observing with Rubin. Would quantum computers actually help, or if they are, in which way, to help us digest and also process all this amount of data?
Yes, I don't exactly know, because I think for the problem of quantum computers, they are useful if you have like a specific problem to solve, and I don't know exactly what that problem in cosmology would be. But I think it would be interesting to try, because I know I have access to very uncertain quantum computers. So I think it would be useful to actually start looking into it, because maybe in 10 years, it will have evolved a lot, and 10 years, that's the end of the LSST. So can we use those future quantum computers to help us with LSST? I think that's a good question to look into. Yeah.
Yeah, and there's actually a related question from AC Online. So still related to big data. You talked about, you know, there's all this like 20 like petabytes data, right, per night. So like, where do we actually store all that data? You know, taken from Rubin, and it's a 10-year survey.
Yes,
right. There's got to be.
Thank you, because actually this picture is from SLAC. This is a picture of the supercomputer that's at SLAC, so the Rubin data are in there. I shouldn't tell you where this is, because like this is precious. No, I'm kidding. And so the Rubin data, so we're expecting 20 terabytes of data per night. They are sent to SLAC, so here, from Chile, and then they are also distributed to one facility in the UK, one in France, and many others as well. But those are the main ones, and so this is where those data are stored. But then they are analyzed and processed to be lighter, so that we can actually like send them around, and it's easier to analyze.
Yeah, question. So when I think of energy, I think of where it's stored at. So like, where do you think this is being generated, stored?
Yes, so the idea is that.
Can you repeat?
Oh, yes, sorry.
Oh, yeah. So the question is, typically, you know, like energy, it has to have an origin, right? Like it has to be like generated, or there's like a conservation of energy. So like when talking about dark energy, where do you think it, you know, like as the universe expands, where does it actually come from?
Yes, the idea would be that it comes from the vacuum in space. So it's the energy of the vacuum that's kind of driving this acceleration. And yeah, that's the idea. But again, this is not matched with actually trying to compute the energy of the vacuum, like theoretically, it's completely mismatched. So we don't know what dark energy is still.
Yeah, all right. We're going to take one last question in person here. Oh, sorry, the lady behind you, sorry.
This is also about data. Will they use maximum amount of data accelerating? Besides physicists and astronomers, what other professions are engaged with the processing of the data? I'm asking on behalf of my principal. I wonder if that should be.
Yeah, great question. So the question was, in the processing of all the, gigantic amount of data, besides astronomers, astrophysicists, and also like physicists, what other professions where people with specific expertise are actually engaged in this process? And, like maybe for the next generation, what kind of opportunities are available?
Mm-hmm. Yes, so there are software engineers who develop the software pipeline to process the data. There are also, I actually don't really know how it's called, but like computer engineer, people who take care of those, this huge amount of CPU, those stack of computers, basically. This is a huge job. It's also like sending those data that is also like a huge problem. And every time people explain it, like within Rubin, I don't understand anything. It's so technical. Those people are extremely talented to like know how to send the data in a fast way. And of course, being an expert in machine learning is kind of useful as well. Yeah.
Yeah, and Rubin is kind of the project where absolutely we expect all kinds of collaboration among different STEM fields because we need everybody's expertise to make something eventually to work. Okay, so last question from online, and this is like from several people. So we know there are a lot of satellite constellations now in the sky.
Yeah.
So how does the proliferation of those constellations affect the viability of Rubin data?
Yes.
Yeah, and how do we actually make sure whatever we get the results, right, is actually like trustworthy?
Yes, thank you. Yes, so indeed, there are satellites orbiting the Earth that are actually they are more visible at dawn or at dusk. And so that indeed impacts our astronomical observation. And there is a lot of study in that in Rubin, how to detect those satellites and how to remove them. But the thing is that there are plans to have even more gigantic satellite constellation around the Earth. And this is extremely scary to us and kind of like we don't understand the reasoning. Why would you want to pollute the night sky? So there is a lot of work in the astronomy community to try to combat those sort of efforts from technology, from technology developments. So there is also, I think there are laws or like committees actually that are like protecting the sky, and we hope they will be able to protect our night sky so that we can all enjoy the results of astronomy.
Yeah, great. And I think that this also highlights where, again, say software engineering is really valued in the process of data processing, because there are pipelines currently being developed to automatically trying to remove all those streaks. But again, we cannot simply just rely on machines. So there still needs to be, experts coming in with, physics and astronomy background, which like to verify those. But again, like satellites are great in many ways, right? Advances our life, but also for our scientific studies, we're kind of trying to minimize their negative impact. Great. So in the interest of time, I know there's so many questions here, but Agnès will be here until the last question is answered in the room. So just to stay afterwards, and let's give her another round of applause. Yeah, and before we wrap up, I just wanted to give a quick overview of what is coming up next. So our upcoming events, including the following. So if you remember, we're doing some local engagement with science from the Rubin Observatory, and the next talk will actually be in collaboration with the Peninsula Astronomical Society. And that's going to be taking place on May the 21st in the Los Altos Library. So that talk is going to be specifically about how to use machine learning to study galaxies and really trying to process, really the enormous amount of data that we're trying to get, which, a lot of the questions are already hinting at from today. And then in early June, we're hoping to have another public stargazing night at our student observatory. Of course, weather permitting, and also based on the availability of the observatory, which is primarily used for teaching this quarter. However, if we are able to actually get an event scheduled, you will get notified as soon as we have a plan if you're on our mailing list. And finally, our next public lecture is most likely going to be in July, and that is going to be on exoplanets and planetary habitability. So again, this is a topic that we specifically picked from the audience feedback. I know there's a lot of interest in this kind of talk, and we are very excited to have already secured an expert to talk about this topic. So if you are, wanting to keep up with what KIPAC is doing, or, just want to engage us a little bit more, these are our social media channels, and also sign up for our mailing list. And yeah, all this information will also be shared with you via Eventbrite tomorrow. So for now, let's bring everyone back to the screen. So thank you, everyone, again, for joining us. And we hope you have learned something really interesting and maybe unexpected about dark energy. And yeah, we hope to see all of you again, and have a good night.